That we wanted to just do the derivation to show how we can prove that if you take the potential to be kq over r, that you'll get the electric field due to a point charge when you substitute in this equation. The derivation is not that difficult, so it's not that really difficult. So let's just go through it in detail. Now you should start asking, you have here partial v by partial x, but here you have r. So where is the x? Where is the y? Where is the z? Well, it's very simple because the r is the distance between the charge and the point that has coordinates x, y, and z. So that means r itself, from Pythagoras' theorem, it's the square root of x squared plus y squared plus z squared. So this is where the x, y, and z are in this formula for the potential. So the rest of the problem is just differentiation. You know how to differentiate a function of x, y, and z with respect to x? That's all what it is. So let's write the potential out in detail in terms of x, y, and z. We replace r by square root of x squared plus y squared plus z squared. And then we'll just write this in a more convenient form by writing it as x squared plus y squared plus z squared to the power minus half. It's the same thing. Now, we want to get minus partial v by partial x, which is the x component of electric field. What will this equal to? There's the minus as it is, and then you have partial v by partial x. What's the derivative of this with respect to x only, keeping y and z constants? Well, the derivative is very easy. The kq is a constant, and then you have the derivative of this bracket to the power minus half. So the derivative of the bracket to the power minus half is the minus half times the bracket to the power minus 3 over 2 times the derivative of what's inside with respect to x only. And you're keeping y and z constants in this derivative. So you only get 2x. And so the 2 will cancel with the 2, the minus sign will go with the minus sign, and you get kq times x divided by r cubed, because this is just r cubed. Basically, if you do the same thing by getting partial v by partial y, instead of getting here x, you'll get y. If you do partial by partial z, you'll get, instead of x, you'll get z. So you can do these if you want on your own, but it's exactly the same. So now we can replace minus partial v by partial x by this. We can replace minus partial v by partial y by this. We can replace minus partial v by partial z by this. And so when you do that, you have kq over r cubed constant. You can take it outside. And what's left is x plus xi plus yj plus zk. What is this? This is just the vector r that points from the charge to the point x that has coordinates x, y, and z. So this is just r vector. R vector can be written as what? Written as r magnitude in the r hat direction. And then one of the r's will cancel with one of the r's, so you get kq over r squared r hat, which is exactly the electric field due to a point charge. So we've proved that if you take the potential to be kq over r and you plug it into the equation that relates the potential to electric field that we took as the core definition in our chapter, then you get the electric field due to a point charge. So that validates the proof that we gave before.